Due to the infinite range of the electrostatic interaction as expressed by the Coulomb force law, electric fields permeate all space. Electric fields are the consequence of charges or distribution of charges. The sketch shows the electric field vector at a point of interest at the location r that is created by a point charge at the location r'. The magnitude of the point charge is q. The distance of separation between the location of the point charge and the point of interest is identified by the vector r minus r'. The magnitude of that vector is exactly this distance. For a positive point charge, this vector also points in the same direction as the electric field at r. In SI units, this electric field vector is given by 1 over 4 pi epsilon times the charge divided by the magnitude cubed of the distance of separation vector times that distance of separation vector. Since field vectors superimpose linearly in line with the rules of vector algebra and according to the principle of linear superposition, this equation can be generalized for the case of multiple charges or continuous charge distributions. The situation for the electric field of a continuous charge distribution is illustrated here. The point charge is replaced by a charge cloud that in this case contains only positive charges. The charge cloud is quantified using the volume charge density ρ, which is a function of r'. Each discrete charge in the charge cloud contributes to the net field vector E. E can be determined by integrating over all such contributions, as shown by the equation at the bottom. Source charge distributions may be three-dimensional charge clouds, and a volume integration is required. They may also be surface charges, so that only a surface integration is necessary. And finally, charges may be distributed along a line, which can be accounted for by integrating along this line. The expressions reflecting these three cases are shown here. This schematic emphasizes the general concept of the direct integration of the field contributions. The electric field at a point of interest P at the location R is in the SI system always given by a factor, 1 on 4 pi epsilon, times an integral over space, which can be volume, surface, or line integral, of a charge distribution ρ, divided by the r² dependence, times the unit vector that indicates the direction of the field at the point P. The charge density ρ can vary throughout the integration volume. R' that identifies the location of the contributing charge also varies throughout the integration volume. Finally, the direction of R' varies throughout the integration volume. It is clear that this is generally a very complicated integration, since it occurs over a vector and it produces another vector, namely the electric field vector at the point P. It is fruitful to apply this concept to a specific charge distribution, for example the charge distribution on the disk of an electrophorus. When we charge an electrophorus like this, and again, what we do is create an electric field above a cylindrical disk, an electric field that reaches out in this direction and also downward. It should therefore be possible to calculate the electric field above the disk. And that's what this problem is about, the direct determination of the electric field above a cylindrical disk. This sketch illustrates the geometry of the problem. Electrophorus disks can be charged negatively and positively. In this case, for simplicity, we may assume that the disk has been charged with a constant surface charge density ρs positively. We place our point of interest, POI, at a distance h on the z-axis centrally above the disk. The disk has a fixed radius of little a. and it sits in the xy plane. This means the position vector r points from the origin to the point of interest, and the vector r prime that identifies the location of the contributing charge is always in the xy plane, going from the origin to that charge. The vector identifying the distance of separation between source charge and point of interest is then r minus r prime, as indicated. In order to determine the electric field vector at the position 00h, we first write down the general expression. In this case, the integral is a surface integral over the surface charge density ρs. The geometry of the charge distribution is cylindrical. Therefore, we use the polar surface element r dr d phi. Since the surface charge density is constant, it can be pulled out of the integral. The integration has to occur over the variables phi from 0 to 2 pi and the variable r from 0 to the radius of the disk, which is little a. In the next step of the solution, we express the integrand in terms of the cylindrical coordinates. Specifically, the separation vector is given by minus r unit vector plus h times z unit vector. Applying the rule of Pythagoras, we find that the magnitude of the separation vector is the square root of the sum of r squared plus h squared. This magnitude goes into the denominator of the integrand cubed. It may be fruitful to verify the integrand using the sketch. The integrand is the sum of two terms, one associated with the r unit vector plus another term associated with the z unit vector. It is possible to remove the first term in this sum using a symmetry argument. For every horizontal contribution to the electric field in r direction, there is an opposing one of equal magnitude. The radial contributions cancel in pairs. Since the integrand does not depend on phi, the phi integration gives 2 pi. Z unit vector and z coordinate h can also be pulled out of the integral. The originally two-dimensional integral has now become a one-dimensional integration with a constant factor, z unit vector, constant charge density, divided by 2 epsilon times h in front of the integral, and an integration over r that has the integrand r on r squared plus h squared to the power of 3 on 2. The result of the radial integration from the origin to the radius little a is given in the red box. The general integral of the integrand is minus 1 divided by r squared plus h squared to the power of 1/2. You may be forgiven if you don't immediately see the integral to this expression. However, you could verify or look up that in general terms an integral dx of the term x divided by x squared plus a constant squared to the power of 3 on 2 is equal to minus 1 divided by x squared plus c squared and the square root of that. This can be verified. What we need to do is go the other way, differentiate. So we go d with respect to dx of this second term here. So that is minus 1 divided by x squared plus c squared to the power of 1/2. If we differentiate that, that's equal to 1/2 1 over x squared plus c to the power of 3/2 times the internal differentiation d with respect to dx of x squared plus c squared, and if we work that out as well, we obtain 1/2 times 1 over x squared plus c squared to the power of 3 on 2 times 2x And if we combine these terms, this cancels with the 1/2, for example, we obtain x divided by x squared plus c to the power of 3 on 2. The result tells us that the electric field vector at the point of interest points upward, and that for large distances h, the electric field becomes 0. Thus, the electric field vector, as shown in the sketch, becomes shorter and shorter as h increases, and is 0 at infinity. This result is in agreement with expectation. Since the total charge q on the electrophorus disk is given by pi radius a squared times the constant charge density rho s, one can also express the field at point 00h as z unit vector times q divided by 2 pi little a squared epsilon times in bracket 1 minus h divided by the square root of a squared plus h squared. Expressing the electric field once more as a function of charge density rho s, an important consequence of this result becomes clear. When the radius little a of the disk is let to go to infinity, the disk becomes an infinitely large sheet of charges. The term in brackets tends to 1 on h, and the electric field of an infinitely large sheet of charges at constant charge density rho s is given by the limit rho s divided by 2 epsilon, always pointing in the z direction. This fundamental result is also of technological importance, since it shows that at short distances from a large sheet of charges, the field is approximately constant, pointing in the same direction. This occurs, for example, in a parallel plate capacitor. The problem illustrates that the solution of the standard problem of electrostatics, namely determining the electric field for a given charge distribution and then possibly also calculating the force on a test charge, can always be solved via direct integration over the charge density. However, this can be mathematically quite challenging. Fortunately, there are other techniques to solve this problem that apply in important cases. They include the use of Gauss's law, the calculation of an electric potential and a derivation of the electric field from that, the use of boundary conditions, and also the introduction of virtual mirror charges.